thank you for inviting me. So here I wanted to, start with this one. I want to give just some acknowledgement. First, I should thank Eric. He defined lots of definitions that I wanted. So there are similar things, and I think these are some of the work that we are talking had some overlapping time, I will say as well. So it is related to the several concepts that he mentioned. The second one is that these are from these two papers. And these two papers, believe it or not, when I was reading it recently, they have written very well. So I don't maybe mention all the details, but you can read it here. And also if there are some references to someone or something that is not in the talk, please forgive me. They are all in the papers. If they are not in the paper, please let me know, we will add it. So that's about things, but I think it should be there. So that's the thing about that. And also these slides are prepared by two of my students, Marina and Jacob. So I edited them, and if it is perfect, good for them, not, again, goes to them. I edited some. And finally, I think one thing that is important, I think I really encourage people to put their talks and also classes online. I have done it essentially for several of my classes, and nothing essentially is like dangerous or something. I have done it for a while, nothing happened essentially. I think, but the people I think use it, and like the students can go and use it. So, and especially with Zoom, it's very easy to do that. If you have a question, please let me know. Okay, so these are the things. And here I try to actually give some high-level ideas. Again, the details you can read it in the paper. But I want to give you some ideas about essentially this kind of embedding board and MPC board, massively parallel computations. And give you some ideas about two lower bounds that are very useful, and this concept which is very important and very related to previous stuff. Okay, so we want to essentially do tree embedding. That is why? Because I think we can solve lots of problems on trees by dynamic programming. And generally, when we have, we have a different algorithm for different applications. Generally, we have large scale data, potentially ordered in dimensions, if n is the number of points. Maybe you can use essentially JL to get it ordered log n. And tree embedding is good because you can essentially, on average, you only need to say who is your parent and what is the date. So in terms of space, actually quite efficient, and especially if you can get a good distortion. And if you have trees, as I mentioned, you can solve almost any problems using trees. So it is very important to have essentially tree embeddings. So what is the idea? So the focus that we have it, say here, we are considering general metrics. General metric can be represented by a graph, or you can consider the shortest path metric of a graph. But here we are focusing more on the dimension, like essentially like the geometric case, like for example, D-dimensional case, Euclidean. And we try to embed those things, and I will say why. And again, this is the idea. So you have this one. We try to essentially, these two nodes, we will embed it into trees, and then we want to get essentially something which is good. And the distortion, of course, is like, we can assume that this is a non-contracting embeddings, and then the maximum distance here over the distance here would be the distortion. So we are assuming essentially they are non-contracting, meaning that all the distances should go up. And we know that tree embedding, this one tree is not possible, because if you consider a single cycle, you cannot embed it into a tree and get a distortion one. So we need to use probabilistic embedding. And probabilistic embedding essentially means that you have lots of trees, and you will take the distance essentially average over all trees. But for all practical application, that is enough, because generally, this is for connectivity problems. You can just solve the problem on each of them and take the best of them. Even for cut problems, there are Rake and others, which is essentially do all of that, and you can solve the same set of problems there. So probabilistic embeddings are enough, and we can get a good result for them. Good. So here, of course, due to Bartal, we know that you can get, or like say the final version FRT, we know that you can get log n distortion if you embed it into probabilistic embedding, probabilistic trees. And this is tight. You cannot do it even for diamond graph. You cannot do better than that. The same generalization, as I mentioned, that exists for the cut problems. Now, that's the thing that we know. Now I want to go to the second topic. This is a very important thing, like probably one of the best things that the people have done it in algorithm design, because you want to solve any problem, trees we can solve it as long as graphs you consider, and then we embed the graph into trees and then we solve it. And generally we pay approximation log n. Of course, this has some its own limitation, works generally for undirected graphs, not for weighted, not for directed ones. Anyhow, let me go to the second topic, MPC. So MPC is massively parallel computation. This is the one that essentially currently is in use at MapReduce, like I think at Google, you say Flume, Hadoop, and especially Spark. Everyone knows about the Spark. And you know all this Zoom, etc. that we are using a Spark. Nowadays, these are like there are even like the biggest startups based on this idea of Spark. And what is the idea is that we want to, so what is the general things that we are considering? Maybe I can go here before that. This is the idea. This is simplest word. There are, the original papers were actually quite much more complicated, but now it is much more simplified. What is the idea? You have a graph or any data that you have it. You will divide it, say, equally between n compute. So you have the total size is n. Assume that the number of computers that you have is n to the epsilon, or some constant epsilon. And each computer has a memory of n to the 1 minus epsilon. So just divide it equally between n to the epsilon computers. And then each of these computers essentially do something locally, and then they just do some message passing to each other. And the only catch is that when they do the message passing, the total amount of data that one computer sends or receives is at most its memory, which is n to the 1 minus epsilon. So very simple and reasonable definitions. And now, what's around is around one computer, like essentially around is one thing that each computer do some local computations. Then they are just sending the data, they shuffle the data, whatever they want. And then the next level, and they send it to each other, that is called the round. And the main goal essentially in MPC to reduce the number of rounds. Because that's the one that really takes a lot of time. And I have actually done some of this at Google myself back in 2017, and you could really see that this number of rounds is super important in practice. So that's a definition of essentially rounds that I have mentioned. And yeah, so you want to find, and again, you want to get space efficient. That is also important. That you want to say that maybe you can increase the number of computers, etc. It is not that desired. We wanted to get the total space of these computers are essentially n, while the number is n to the epsilon. What else? I think that's it. Oh, one other interesting thing, except maybe for some, I don't know, cooked up, maybe not that cooked up independent set, for example, I don't know that much that if you do something extra on one computer, like even exponential, generally we assume in practice that it's linear. The space, the things that these computers are doing are linear in their space, or almost linear. But I don't know actually that many problems that even if you can do exponential in each step can help you that much in terms of the number of rounds. I can create one problem like independent set, some approximation is there, but not for a real problem. We don't know that much. Lots of things we don't know about essentially about this model, which is a very practical, as I mentioned. All this cloud computing are essentially based on some kind of a Spark nowadays. Okay, now coming back to this one, what is the goal? The goal is that we want to get this embeddings essentially into, we want to get this Bartle embeddings, or essentially probabilistic embeddings, into trees, which are very useful, using this model of MPC. That's the whole goal. Good. So, as I mentioned, there are lots of work. I think this was the same. This was the first paper, but there are lots of, actually some of them by us, and then lots of other people as well, that they are improving this, and especially on this clean model. The first one was not clean. This model is very clean, actually. So the result that we have is here. I cannot go to all the details. I just want to say some interesting thing about it. And as I mentioned, I think the papers are well written. At least when I read it now, I could understand it. But yeah, so that's the interesting thing. But here, we have a set of endpoints in d-dimensional geometric space that you want to essentially encode it into some tree embedding. You want to get the, so this is the thing. We will get the distortion log n to the 1 minus, log n to the 1.5, with probability at least, almost, high probability in MPC. And this is the idea. The idea is that we will get it space efficient. So space efficient means ND total space. You have n points, each of them have d dimensions. You need ND. And then, this is important. This is the best version of that, essentially. I mentioned n to the epsilon computers, each of them n to the 1 minus epsilon. But of course, you can define epsilon prime to be 1 minus epsilon. And in that case, maybe it's essentially when when the memory per machine is n to the epsilon, essentially you have lots of computers, but each of them have very small memory. That's generally the hardest regime for MPC. And why? Because otherwise you can just combine some of these guys and then make it simulate bigger guys essentially doing the smaller guys. That's somehow the idea. So this is the hardest case. We will get it here, and this is order 1 round. And by the way, these are the papers that I have mentioned of Alex is here, and there are some other co-authors here as well. And what do we get here? So this is the one that we will get it essentially for this. And also we will get a similar theorem for JL, because JL is another very important embedding. That is actually, the problem is easier there, I will say. It's not that hard, but it is interesting. We can get almost tight result for JL embedding. Here we don't have the tightest result, as I will mention, as we wish. But for JL, actually, we can do it, the fast JL using fast FFT, essentially, we can get it, and we can get it almost with optimal bounds. You can look at the paper and see the bounds. But this is the one that I wanted to talk about it. And let me just give you some ideas about it. This is the, again, high-level ideas. Please read it. There are lots of details. Here, this is this kind of Aurora grid partitioning. Well, I think, I think Baker has done that also maybe for planar graph, but maybe this is more to Aurora's things. And I think Eric already mentioned the ideas. The idea is that we will consider these things, and then we will consider the whole big grid. And it is a random grid. And then, we will just essentially make it, this is like more quad trees, essentially. We will do that as long as there are some points here, and then we will just recurse on that, such that in each part, essentially 1 point remains. So that's the idea. So you will consider the whole point. We have a big grid, you will divide it, and then if there are some parts that are more than 1, you divide it again, and so on and so forth. That's essentially very good. And this is and the only thing is that you need to have some random shift to do that, so everything becomes good, essentially. So that's about this one. And then there is Aurora's, so this is and how do we form the trees, essentially, is easy. So, here, we have essentially one big node, essentially here, for each of this, division or quadrant or something. We will put a node as long as there is at least 1 point here. And what are the weights? This was the thing that Eric mentioned. So what are the weights that you will put it? Different weights you can put it. The one that you can use it, for example, square root of d is the dimension times some weight which decreases geometrically. So that's, the weight is important, but that's the thing that you can put it. And you can get essentially a tree. And again, if some place there is no point, then you don't continue. You will empty that. There is another one, Charikar et al. Ball partitioning, that they have done it actually to de-randomize Bartal. That was the main things. But the way that they are doing it, is a bit different. So but they are doing this kind of grid partitioning, as I mentioned. But they are adding balls. How do you do that? On the center of this grid, they are essentially doing balls of, say, radius, I don't know, half of the grid size, or half of the cell of the grid size, or width of the grid, or maybe 1/4 of it. So it is important because these balls you don't want to intersect. But, okay, they don't intersect, but the issue is that now each of these points may essentially go to some of these balls. The issue is that you may not cover all balls. All points. So how you can resolve this issue, you need to repeat this process. And again, all of these are with these random shifts, to make sure that, and each point will depend, essentially will go to the first ball that covers it. So these are the two approaches that exist here. And again, the way that we are doing it is a similar thing. All balls that are having this, like have at least one point, that would be a node. The weights would be similar, and then if there are more points in one of these partitions, you will recurse. So the way that we are doing essentially is the hybrid partitioning, and that's the interesting thing that is about our work. And so what's the meaning of essentially hybrid partitioning? I will mention the algorithm. But in some sense, when we consider the whole things, we are dividing into the same thing that, we are doing similar to Aurora, we make it into grid. But on each of these cells, we are actually running this kind of a ball partition. Let me, so this is like cylinder. It is combination of essentially a sphere and the cube. That's somehow the ideas. Let me, just go there. This is the exact definition. So, so we are doing this kind of bucketing dimension. So what do we do that? So we are essentially given some data with dimension 1 to d, and here are the number of buckets that we want to do it. We will divide this dimension into r buckets. Now, given each point x, you will essentially project it into each of these buckets separately. So, into this first set of coordinates, second set of coordinates, and so on and so forth. Now, for each bucket, you are doing a ball partitioning. So you will just do that. You will do it in different things. For each of them, you are doing the ball partitioning of Charikar et al. And how do we recurse? You can define, consider any 2 points. Note that we consider all points, and then for each set of dimension, in the subset of dimension, we will embed it. For each of them, we are doing this kind of ball partitioning. Now the question is that how do you recurse? 2 points you can define will be essentially in the, so these are how do we form the partition. 2 points will be in the same set of the partition, if and only if they are in the same essentially ball in all of this projection that we have. So those guys will be in the same bucket, and for those guys, we repeat this process. Now, what is the interesting things about this approach? So the interesting thing about this is that if r is equal to 1, essentially, that would be just Aurora's things, essentially, regular grid condition. If r is equal to d, then it becomes Charikar approach, because we are just doing ball partitioning. Interestingly, in this work, we are doing r equal to log to get the result. So I think so. This is a sequential algorithm. So we have essentially a cluster that is corresponding to all trees. You will bucket or dimension. For each bucket, we run a ball partitioning, and then for each maximal set of vertices containing the same ball, for all buckets, we create a cluster, and then essentially we recurse. Good. Yes. Okay. So why this is good? So just to give you just some ideas. Again, lots of details you can read it in the paper. But this is somehow the intuition that somehow Aurora approach is very good. Why? Because all these are deterministic. You know what is the width of each of these, and you can just essentially, like a priori, you can give this one to all machines, and they know everything for computations. So it is very good for computations, essentially. The issue with the ball partitioning is that it is somehow is sequential. because like this, you are doing this, maybe this point is not covered, you need to do it. So it is sequential, and if you want to give all possible cases to the machines, the space would be too much. Somehow, this is the approach is doing in between, some kind of trade-off when you do that, and you can make the space per each machine efficient. That's somehow the ideas that we are doing here. So yeah, this is the idea that I want. I think that should give somehow the general idea. And as a result, we have this problem. So we have for grid partitioning, if you do Aurora essentially, the number of rounds would be order 1. You can just give it, I mean, you can essentially give all this kind of partitioning to machines and everything would be good, but the distortion would be like n to the 2. If we want to do ball partitioning, then in that case, the distortion would be this. And you can get the round order 1, but then the space would be too much. It would be not space efficient. So this one that we have essentially log n to the 1.5. The number of rounds is order 1, and the space is okay. Actually, it's space efficient. So there are some interesting problems here. I wanted to just mention and just mention some one other interesting problem in the same domain. So the first thing is that I mean the open problem is that can we get this log n like 1.5 to log n? Below log n is hard because essentially that implies something for Earth mover distance essentially that. It is hard. The people have worked on it and they couldn't get it. But log n is a possibility. But we work hard actually. It's not that's not easy, but it is still possible. Another interesting thing. We discuss all of this for geometric, like essentially geometric or Euclidean case. So one may say, why do you consider this? Why not for general metrics or a graph? The issue is that there's a lower bound about 1 cycle, 2 cycle. So if you have this is in MPC, that this is a 2 graph is given to you. One is just 1 cycle of size n. The other one is 2 cycles of size n over 2. The question is that can we understand whether this graph is 1 cycle or 2 cycle? That so far the conjecture is that we cannot get anything lower than log n rounds. The people tried. We don't know in terms of lower bound. The base lower bound is say that maybe, I mean, constant or like a little bit super constant is not possible, but it is not close at all to log n. So there's a very big gap here. And this problem of Barthol essentially for general metric, like a sparse graph, that would be, if you want to solve it, because at least you need to say that this is, like if there are 2 cycles, means that the distance between these 2 guys is infinity. So that problem should solve this problem, and we cannot, get any result. However, this still works for if each of these points that are given have essentially dimension n, we can embed any metric into this, and then we can get all these results. And this is it is maybe actually too good to be true, but it is not the case because somehow we are cheating. If the original size of the graph is if they have n dimensions, then the total size would be n squared. So it means that we have a lot of space essentially to do MPC. Anyhow, so that's one thing. Can we improve this one? The other issue is that the problem itself actually is also interesting. We will show this one. This is like essentially pasting 2 results together. What about if you don't want to do MPC? If you just want to get for geometric case, you want to embed it into trees. Interestingly, there is a lower bound of SQR root of log n, but we don't know anything better than log n, the same thing that Barthol obtains. So there is a big open problem here. Can we improve for geometric case? Can we embed it into trees? I mean, potentially with SQR root of log n. SQR root of log n, you cannot do better than SQR root of log n, but maybe SQR root of log n is possible, and no one has done it. I think that would be a very great open problem to solve. Good. So this one that I mentioned. So I mentioned about this 1 cycle, 2 cycle. I want to say also one other thing very quickly here. This is another recent paper that we had about this orthogonal vector conjecture, and another important problem in MPC. So what is the for the lower one? What is the orthogonal vector? So you have a set of n binary vectors. You can think about the size of them is log n, And you want to say whether there are two of them that A times B is equal to 0. So there is no truly subquadratic time for this problem. Like you cannot get essentially n to the 2 minus epsilon for some constant epsilon. And it's a very well studied problem, and it is the interesting thing is that lots of problems now you can show that you cannot get these problems better than essentially quadratic times because of reduction to this problem essentially, orthogonal vector. And as I mentioned, for the MPC world, there is this single, very simple problem, 1 cycle, 2 cycle. Just think about it, it's like very interesting. By pointer jumping, actually you can solve it in log n rounds, but you cannot do anything better than log n rounds. I mean, at least so far. Whether this is 1 cycle or 2 cycle in the graph. And you have order n and you can do that. This problem has been used a lot, for example, in this paper to show lots of other problems. For example, in MPC cannot be done better than log n rounds. And again, number of rounds is super important, so that's a very important practical thing. However, that was so far that was the only other problem. This is the conjecture that in the second paper that I have mentioned, we have it. This is the MPC orthogonal vector conjecture. That actually, with that we can also prove several interesting results. It says that if you have a space efficient, the way that I have mentioned, a space efficient means order n total and each machine has n to the epsilon. Essentially, if you want to, this orthogonal vector problem, if you want to solve in MPC, a space efficient, you need n to the epsilon processors. Note that the previous result says that you cannot do better than log n rounds. Here I'm saying much stronger, I'm saying n to the epsilon rounds. So if you want to solve essentially this problem efficiently, you cannot get anything better than n to the epsilon rounds. And what is the idea? So why do we think that this might be true essentially? This is just essentially conjecture. The idea is this one. So consider essentially n vectors. Say the size of them is log n or essentially little, like O tilde of 1. So there are n vectors. To see essentially that whether two of them that are like essentially the multiplication is equal to 0 or that product is equal to 0, you can consider n choose 2 here, which is n to the 2. Now let's consider this case. So here we have good. So we have n to the epsilon processors. The idea is that the only way that you can solve this problem is that you send at some point two of these vectors together in one machine, such that that machine essentially can multiply this and say it is either 0 or not. There is no other way than this. So how can you do that? Like now, let's see if it is the case. So if this is the algorithm, that is the best thing that you can do. So you have n choose 2 essentially pairs that you need to see the multiplications, n square. Now, how many machines you have n to the epsilon? How much space they have n to the 1 minus epsilon? Which means that each of them can do n to the 1 minus epsilon choose 2 essentially pairs. So in one round would be essentially n to the 2 minus epsilon times n to the epsilon. So in each round you can do it n to the essentially n to the 2 minus epsilon, correct, n to the 2 minus epsilon essentially of these pairs. So you need at least n to the epsilon rounds such that you can do everything. And of course, this is just a conjecture. We don't know you can do anything better than that or not. But I mean, so far, like we tried. Again, it would be good actually somebody refute this. We'll be very happy if it is the case. Yeah.
What's the last sentence about constant length vectors? I mean, are you talking about vectors of constant dimension? Or?
Which one?
The last sentence. Vectors are constant length.
This does not improve the non-complexity of any algorithm. Yeah, I think by here essentially means constant length means logarithmic length. I think even for constant length, constant like because in the this kind of orthogonal vector, you know that the dimension of each of them can be log n. But even I think for constant, we don't know anything better than that.
And OV, you mean over Boolean or over reals? Or,
no, this is the orthogonal vector. So this one essentially, I think this one, I don't know what is the best restriction, but I think maybe even where integers, you can say this problem is hard. Maybe even a small range of integers is still the problem is hard, in general. But anyhow, so this is, I think, the last one that I want to say. And essentially, there is this kind of reduction you can say. Any problem that you can reduce to this problem, you can show that it is hard as well. Of course, assuming the a strong OV conjecture. And OV conjecture, I mean, we know because of the relation to essentially set a strong satisfiability hypothesis, that it is, I mean, the people believe that, I mean, it might be true. But here, this is a stronger version of that we talk about the MPC. And this is a simple, I mean, as long as you can do some gadget things locally, then, and you can reduce that problem to this OV things, essentially, you can say that problem is hard. As a result, you can say actually lots of problems are hard. For example, some famous problems are diameter, graph diameter. So you can say that using the graph diameter, we can show that that also needs n to the epsilon, for example. Even for a sparse graph, it needs n to the epsilon rounds. Or another interesting that we show is the longest common subsequence, or edit distance. These are the problems that you can do with dynamic programming, and if you want to do a space efficient, you cannot do it better than n to the epsilon. However, if you don't want to do it space efficient, then, and you get approximation, then you can get actually better than log n, even constant number of rounds. But space efficient, you cannot get it. And this is like, I think generally this is just one example that I have mentioned for diameter. It's a simple one essentially. You can, if you have say these vectors A and B, you want to see whether one vector from A times a vector from B, set B, essentially their dot product is 0. How do you do that? This is a very simple reduction. You can just you can turn this problem into a diameter problem. And how do you do that? So for each of these vertices, if it is 1, you will connect it to set D. D is the set of dimensions. And if it is 0, you don't connect it. And then there's the one vertex SA that is connected to everything, SB that is connected to everything, and you will put an edge there. You can show that if the diameter of this graph is 2, then the dot product, there is 2 vertices, that the dot product is 0. And if it is 3, it means that there is no such vertices. This is a simple thing that you can see it also in the paper, the second paper that I have mentioned. And everything is recorded, so you can find. This paper is this SPA, 2024. And the paper is on archive. Good, so I think that's it.
Questions?
Yeah.
So you defined this MPC version of orthogonal vectors. Have you considered is there like a natural version of there's probably just a natural version of a Kitting set in the same way for MPC. Have you considered that?
Yeah, but I mean that is
because it sometimes gives you some problems. It gives you more flexibility than orthogonal. But like for EMD, you can sometimes prove better lower bounds if you're like conditioning on Kitting set.
Yes, actually we didn't consider that would be a good thing. Whether we can get anything better than that.
Okay.
I mean, this is the first thing. I mean, we can get.
Right.
I mean, as I mentioned, these are more inspiring talk. Essentially, I didn't want to the end of the things. No, this is just these are the results that we have done. They have not been easy. Maybe at the end, some of them looks easy, but they have not been easy actually. Especially about the embedding part, it's quite actually involved. But but we don't think that it is there. I mean, at least I don't think that we are there. I think we can get some improvement. Probably the most interesting problem is that, as I mentioned, getting that for 3 probabilistic embedding of like Euclidean 3-dimensional things better than log n, better than Bartal. And there is a lower bound of square root of log n, but there is a big gap here. We don't know. I think Asaf actually had the paper on that one, some related problem to that.
The lower bound for you.
Yeah.
Other questions? Right. If not, then let's thank Mohammed again.